This is part 6 of lecture 11, ELEC5300. I'll be talking about how to solve the maximum variance formulation or principal component analysis. Let's set up the problem first. Again, we have observations x of n, where I have capital N of them, and each one of these is a d-dimensional vector, and my goal is to represent each of these d-dimensional vectors with a smaller number of parameters m, right? And I want to make sure that I can do this while kind of maximizing the variance of the projected data. And so the first thing is I'm going to have a bunch of data, which I'm going to, let's say, plot in just a 2D space because it's easier for me to draw that than some higher dimensional space. So let's say I have a set of data over here. So I have data, something like this. And what I'm going to do is I'm going to first say, well, I'm really only interested in the mean or the difference between each data point and its mean. Right? So I'm going to call this data point here x bar. And so each of these little x's here, I'm only interested in just approximating that little line here because I know they're all going to be somewhat close to this mean value here. And the mean value here I can just calculate by averaging all of those data points. And this is just the sample mean. Right? So now what I want to do is I want to find then some way of saying I'm going to start from here and I'm going to stay in a subspace and move as close to these data points as possible. So I'm going to start by considering the case where I'm only interested in the one-dimensional subspace, right? And so that says I'm going to move in a certain direction. Let's say it's going to be this direction here. U1 in order to approximate this data point. So for example, if I want to approximate this data point, I might move along this thing all the way over to here or something like that. Okay. So each data point then is going to be approximated by some x tilde, which is just starting from x bar and then moving along this vector by a certain length, where the length is alpha sub n1, right? So since I'm only interested in this, the direction of this u1, I'm going to assume that u1 is unit length. And so alpha is just the distance that I travel in that direction. Now, how far do I actually travel in that direction? Well, let's just take a look at another situation where, okay, let's say this is the mean. Right. This is the direction u1. Here's my data point x, or x sub n. I'm going to project this one down onto this point here. This is my x tilde sub n. And then this distance here is just alpha sub n1. It's just a distance to get as close as I can to xn along this direction u1. Now, if I say, well, here's a vector here like this, I want to find this one here where this is 90 degrees. You say, well, all I'm going to do is then take the dot product between this vector here, which is defined by xn minus x bar, right? So this vector here is this one here. And to find this distance alpha 1, I'm just going to take the dot product between this direction and this vector here to get this distance alpha sub n1. So that's given by this equation right here. And now if I had chosen this x bar to be the mean, then I know I'm either going to move in this direction here or I'm going to move in the opposite direction. Right? And so here, if I look back to here, if I choose the x bar so it's the middle, then I'm kind of equally likely to go in this direction as I am to go in this direction. And so it's not surprising that you'd expect the mean of alpha sub n1 to be 0. And so we're interested then in the variance of the projected data. And it turns out that that's given by this equation right here. This is a quadratic form where this is the direction that I'm talking about. And this s matrix is the empirical covariance matrix. So it's the covariance matrix computed from the data. So this is x minus the mean, and then I just kind of square it, and this is going to be some kind of square matrix, an n by n square matrix. And so if I kind of draw this figure out graphically, S is this thing here, right? It's n by n. And then U1 transpose is this, it's n-dimensional. And then I multiply by U1 over here, right? And then when I do that, I'm just going to get a scalar, which is the variance. So how do I know that this is true? Well, I can just simply compute the variance of these alpha sub n1s. I do that here. Remember the variance is 0. So the mean is 0, so the variance is just the average value of alpha sub n1 squared. I'm going to substitute in the formula that I got over here for alpha sub n1, dot product that I got from this analysis over here. I'm going to note that this is just a scalar, right? So I can take its transpose, I'll get the same thing here. So I can just take this times its transpose, it will be exactly the same thing. So the transpose of this, so I take this, and I multiply it by its transpose, which means I'll just take this transpose times this transpose over here. And then I'll just move the u's outside because I'm summing over n. So I'm only summing over these things inside, so I can take the u's outside of the sum and outside of the sum here. Right? I'm going to put the n inside the parenthesis, and this is just the empirical covariance matrix that I talked about before. Okay? So now what we want to do is we want to maximize the projected variance, which is given by this part of the term here. Subject to the constraint that this has to be a unit norm vector, unit length vector. And so that's a constrained optimization problem. I want to make this thing as large as possible while keeping u having length 1, right? Because the easy way to make this large, no matter what u is to just simply make u bigger, right? If I make u 10 million times longer, I'll actually increase the value of this by 10 million squared, right? So to avoid me playing games like that, I'm going to have to keep this one equal to length 1, right? And so I'm going to do that constrained optimization problem by using Lagrange multipliers. So this is my constraint. My constraint is U1 transpose times U1 is equal to 1, or moving this over to the other side, 0 is equal to 1 minus U1 transpose times U1. And so I'm going to take my constraint here and add it into this function here by a Lagrange multiplier by lambda 1, and I have to set this thing, I have to differentiate this one with respect to U1 and differentiate it with respect to lambda 1 and set the whole thing equal to 0. Of course, when I differentiate with this with respect to lambda 1, then all I get is that this is equal to 0. That's just my constraint. So really, the key thing is just to differentiate this with respect to U1 and set the result equal to 0. And so, if you don't remember this kind of analysis, I go through a short review of constrained optimization in the next part. If you do remember this, then you can just skip that part. So let's differentiate this with respect to U1. Remember, this is like a quadratic, so this is like SU1 squared. So when I differentiate this one, I just get 2 SU1. I differentiate this is just differentiating with respect to U1. This 1 goes to 0, and then this is like U1 squared, right? So this is kind of like when I differentiate this, I get a 2U1. right? So times lambda, so I get 2SU1 minus 2 lambda 1 U1 is equal to 0. I can move this over to the other side, divide both sides by 2. I get this equation here. This is an eigenvector equation. And this is where the first time we say, hey, didn't we see something like this before when we were talking about Carhoon and Loew transformations? And yes, sure enough, we did see that. So this is our first hint that there's some kind of whitening involved in here. But because we're only looking at one variable, there's really nothing to compare it to or to uncorrelate it from. But anyways, U1 is an eigenvector of S, right, with this associated eigenvalue, right? And then you can say, well, what is the variance of this, right? Well, the variance is just this, so I can multiply by U1 transpose, and when I do that, I get this, and now lambda 1 I can pull over here. I get U1 transpose times U1 is just the length of U1 squared, which I know is 1, right? That's the subject of the Lagrangian constraint. So lambda 1 is just the resulting variance. So this eigenvector just tells you the variance of the component that's in the direction U1. And that's exactly the same result we got with the Carhoon and Loew transformation. So therefore, to maximize this variance, because I am interested in making this variance as large as possible, I just have to choose the lambda 1 to be as large as possible. And the lambda 1, I don't have free choice over this. So lambda 1 has to be an eigenvalue of the covariance matrix. So I just have to find the eigenvector of the covariance matrix with the largest eigenvalue, and that is the first principal component. So in the case where we're interested in more than one direction, we can simply start out with an iterative approach where we just start with the first eigenvector, which we found before, and then we just add additional principal components. And so the key point here is that we need to choose a new direction which maximizes the variance along all the possible directions orthogonal to those already considered, right? But if you recall, the eigenvectors of the covariance matrix are orthogonal to each other, right? And so they also then would maximize the remaining variance, right? And so in the next case, if we were, for example, interested in when m is equal to 2, we would just choose the next eigenvector corresponding to the next largest eigenvalue. And then by induction, we can show that if we're interested in m-dimensional projection space, we just choose the m largest eigenvalues and their associated eigenvectors to define the principal subspace.